Welcome back to the late afternoon session of talks. In this session, we have 3 short talks, about 30 minutes each, and they all focus on extremely interesting topics. Our first speaker will be Carl Brumund from Dyn, where he's the principal network engineer, and he'll be talking about designing and building large data centers, not Google large, but large.
Thanks. So I wanted to come and talk a little bit about data centers, what we call sort of a small, because in the past we've had people like Microsoft come up here and talk about how they've built theirs, which I think are about the size of the hometown that I grew up in. So we were on a slightly different scale, and some of the things that we did a little bit differently for that. Right, it's the green button. So we're Dyn. You probably know us from DNS. Kind of been doing that for a long time. We also do email, internet intelligence. If you want to know what that is, hit the website. Come ask me later. What we've got about 28 sites around the world, hundreds of probes, and we're in a bunch of clouds as well. 4 core sites, and we're building out regional cores that are going to follow the same model that I'm talking about today. They're building those in Europe and Asia Pacific. So what this talks about is basically a new core sites that we're building the network for those. So first I want to talk about what not to do. So with every success there's always the learning experience along the way. As Doug Adams has that quote there. So the first design that we came up with was basically like this. Pretty standard. It's a CLOS design. That sounds fabulous. It gives us redundancy, lots of bandwidth. It looks good. Let's go. We're going to go to the vendor. Let's place a big order. We'll buy a bunch of stuff. We'll rack it, stack it. Let's jump on the CLI, start configuring. I mean, what could possibly go wrong? Well, we had to come up with logical. So let's use MPLS because just like BGP solves every problem, MPLS also solves every problem, right? Something like that. So we'll do MPLS VPNs. Our top of rack switches are going to be PEs. Sounds good. Yep, they support MPLS. Oh yeah, that V6 thing. Yeah, 6VPE. Yeah, that didn't quite get supported. So then we kind of asked, and it's like people writing this sort of said, well, V6 wasn't a requirement. What? Huh? So unfortunately, even Bert was ashamed of us. So that's it's a little bit embarrassing, that part. So kind of what we had to do is sort of, let's do sort of a bit of a start over again. Or, I kind of like to call the previous, sort of the BK before Carl time. So, let's actually, maybe we'll actually engineer it this time. What a concept. So we thought first thing we do is let's actually define the problem, what we're trying to solve here. So we had some legacy DCs, and they're all right, they're pretty good, but they weren't great. We didn't have enough bandwidth, didn't have enough redundancy, didn't have enough security. Very traditional, but it's kind of the old school design. And we had a lot of legacy servers and so on. So a lot of stuff that we're doing is almost more brownfield than greenfield. We're not basically starting from scratch. We've got to accommodate a lot of stuff that's legacy. And the other thing is we're not building DCs that are going to have 10,000 servers in them. So in our particular case, it just has to be good enough, fast enough, and cheap enough. So it's kind of, it doesn't have to be perfect for anything, and we're going to try and find that sort of that sweet spot there. And in terms of size, this is really pretty small that we're doing this. We're starting out with 20 racks. Which by now are actually full, so we're already kind of looking at the expanding. So we're thinking, 20 kind of growing to 200 order of magnitude. Need something kind of handle in that range. It's a little bit different than handling the 10,000 racks. So let's kind of get some requirements here. So kind of had to be good. So it's main thing is kind of it's scalable, and also the fact that our existing teams can support it, because it's really cool as an engineer to come up with all sorts of neat things, and hey, the vendor has a new knob, let's turn that one on. And unfortunately, sometimes it's not something they can support. So it kind of had to be something that can be easily supported. We're also really big on using standard protocols. So we didn't want anything that was proprietary. No specific, one vendor's fabric implementation or something like that. We don't want to get locked into something. If something goes wrong, we can always change out later. We can upgrade or whatever. Fast, So in our particular case, 10 gig, we're not the 100 gig levels. So 10 gig, multiple 10 gigs, okay, pretty easy. Cheap, so it's basically can't cost a fortune here. We're not in the networking business. The network's basically to serve the rest of our stuff. It also had to fit us. So right now, one of the popular things to do is overlays. Unfortunately, we've got a lot of legacy and bare metal servers. Putting that in overlays, yes, we can do it. We can't do it easily. We can't easily move them to VMs because of our developers. And the other thing is, the thing had to work, because I'm really getting too old to be paged at 3 a.m. This just really sucks. So I just want it to work. And the main thing is it kind of had to be better than what we had. As Joe Abley kept telling me, just make it better, Carl. So the kind of things we had to figure out here. I mean, it's a lot of the basic stuff. Let's actually make the routing work this time. Including that that V6 thing. Security again. Make it better, Carl. And service mobility. Kind of one of the things is we want to make sure that anything that we do, we can still migrate and move services around. Why? A server dies, or a VM dies. Oh, we've got capacity in another rack. Make sure we can easily move it over to that. So physical design, version 2.0. Hey, see the design version 1.0. Yeah, it's also called the boss saying, we don't have any more CapEx left to buy this all over again, so can you make it work? Yeah, I think I can work with this. So it's, main difference is that, we're not going to do the MPLS, but basically everything else looked exactly the same. Didn't really have to recable anything. So still pretty standard. It's class. We like that. We can scale it horizontally very easily, so this fits this growing from 20 to 200. Yeah, okay, I can work with this. Now, the logical design. So our legacy data center was very traditional, layer 2, layer 3. In my mind, way too much layer 2 because almost any layer 2 is way too much. So we like layer 3. It just works better. It was just easier to troubleshoot. So one of the things, of course, is, we get in that whole service mobility thing. So, okay, we'll have to figure that out. And the other thing we want is, we don't want to put everything on the internet. We don't really need routable IPs for our databases and other stuff. So, okay, I guess we're going to need multiple routing tables then. Well, the whole MPLS thing didn't work, but hey, we've got this, VRF Lite or, routing instances we can do. Okay, yeah, that would work, but then we're going to have multiple IGPs if we run IGP, multiple BGPs. Okay, we'll think about that. Now we get into, remember, we bought really cheap layer 3 switches because it had to be cheap. So how about rib and fib scaling? Is that going to be a concern? Well, so I have to think about that. Oh yeah, we're still not ready for the overlay network, so that's still some point in the future. Or, as I like to say, that's going to be make sure I have some work in 2016 and I don't get laid off. Because, it's always important to have, the next project. So we thought, okay, so we're going to do this multiple routing tables. Well, how many do we need? Like, are we going to have, 2 or a whole bunch of them? So we kind of came up roughly with about this list. Internet accessible, pretty obvious. The stuff that's going to be out there, the internet needs to reach. Stuff that's not internet accessible. Oh, okay, that's pretty easy. Well, we also have hardware load balancers, and we want to have stuff behind them. We tend to use our load balancers in line. It just works for us. Again, that whole stuff that our NOC is used to and our ops teams are used to and they can support. That's how we operate. Okay, let's keep that. Well, that means we're going to have a separate routing table for the stuff behind our load balancers. Okay, there's 3. Between sites. So this was a kind of a late addition because initially I thought, no problem, I'm just going to extend each of these existing ones between sites. And what I soon realized is that going between routing instances causes a problem. You wind up with asymmetric traffic in the sense of where do you jump routing instances. I'll talk a little bit more about this later. So basically the short answer was, let's just create one between the sites. That makes life easy. We also want to sort of test one that we don't want, we can't really use that the big test network called the internet all the time, only some of the time. So okay, so I'll have a QA set up. And we've got a whole bunch of stuff that are what we call common systems. This is a lot of our continuous integration pipeline, stuff like our Git, our Chef, Jenkins, NTP servers, recursive DNS servers, a lot of those things. And we want them accessible by both our QA environment and production. We don't want to have QA accessible to be able to access production. Okay, so I'll be a 6 one. Okay, 6, it's more than I was hoping, but I can live with 6. It's not a huge number, it's not double digits. Okay, so reasonable. So logical design, because pictures kind of are worth 1,000 words. So we did something like this. The lines that you see between boxes are effectively bundles of 10 gig links that are trunked, so with sub-interfaces. So we did everything as point-to-point links between them. And basically just try to show the different routing tables here in different colors, just for some clarity. You notice that remote sites we have connect 2 different ways. In some cases we have direct connectivity, as in we buy a layer 2 circuit from somebody and we can just run it that way. Other times we don't have that connectivity because it's just too far away, the site, or the site's not big enough and it's not worth the cost, so we'll just run IPsec tunnels. So we have basically 2 ways to get there. You'll also notice that not all of the routing instances are extended everywhere. For example, the intersite one never needs to go to a top-of-rack switch because no server will ever be in the intersite. And also, the load balancer does not need all of the routing instances as well. Now, one of the things we had to also decide is, are we going to do an eBGP or an iBGP? Now, in the past, we've had Microsoft back in NANOG 55 talk about how they use eBGP as their, effectively as the new iGP. I think that was the name of the talk back then. So we looked at eBGP, and one of the concerns we had is that we're going to have a whole lot of sessions because you're going to have every top-of-rack switch will have an eBGP session to the spines times the number of routing instances. So, it winds up being a substantial number. If we lose a single link to a rack, then there's going to be a whole lot of sessions that are going to flap. So we weren't really sure if the eBGP is really going to be the right thing. We had concerns about it. We didn't actually test it to see whether or not it would work. Maybe it would. Your mileage will vary. Instead, we kind of decided, let's do iBGP. We can use a route reflector that scales. There's a talk this morning about the iBGP stuff. We try to sort of incorporate a lot of those best practices that I talked about. And the other nice thing about the iBGP is our staff actually understand that model. This again gets back to the whole thing about support, so somebody else can handle it at 3 a.m. and I don't get paged. So, okay, iBGP will work for us. And the main thing is for the iBGP with the route reflectors, total number of sessions is kept under control because it's specifically our spine switches are the ones that we're most concerned about the load on those. So then we kind of had to pick a IGP, and this was kind of like a whatever. I mean, really anything would have worked here. So we went for the easy and the obvious choice, OSPF version 2, OSPF version 3. Why? Because our staff understands OSPF version 2. So it just makes it easier. Really, could have done ISIS, except for the fact it's really hard for us to hire ISIS experts out of the ISPs. So that's not really that good. Could have done OSPF v3 for both v4 and v6. However, based on this draft, IETF draft, that was kind of discouraged. So like I said, we went with the obvious choice. In the end, this really doesn't matter. Now, one of the things is when you have multiple routing tables, you need to get between them. So if we have a web server or DNS server or an API server in our public routing instance and a database in private, the two will not want to talk. They may be in the same site, they may be in different sites. So one of the things you have to do now is you have to do route exchange between them. And as was discovered, this can really get confusing fast. So what we did was we basically said, hey, BGP, communities, there we go. Everything tagged with this community is this type of route. We import, export that way. Again, using the VRF Lite, in our particular case, instance import. Almost everything is done on the spines to basically, that way reduces the number of hops that things have to travel. It also gives us the maximum bandwidth because of ECMP. So, and everything keeps symmetrical. There's a couple exceptions to that, but almost everything, well, being on the spines between the RIs. Now, once you start doing multiple routing tables and doing route exchange, yes, I do have the same route in multiple routing tables, so therefore my total number of routes grows. Again, the whole rib concern for rib scaling. We've run some numbers there. Based on actually the routes that we're seeing right now, it's actually pretty okay, and we were expecting to actually have to upgrade our spines to ones with larger memory, and that's actually something that we can actually push out just because we're not seeing the route table growth as high as we were at first fearing. So one of the things when we did iBGP, and we talked about this, talked this morning on route reflectors, is the route reflector will only ever give you a best path. Okay, well, we soon realized that we have a failure scenario. So in our particular case, we deploy a pair of top-of-rack switches. Servers are connected to both top-of-rack switches. Those top-of-rack switches basically announce the routes to the route reflector, which then sits on our edge MXs. Yes, we're a vendor JShop. And then the spines are clients. So the spines will only ever get a best route. Well, what happens if the route that the spines get, they can't reach? Well, then they'll probably follow default, go back up, and we can wind up with loops. Maybe eventually the packet gets there. So that really sucks, because asymmetric routing and loops, and it's all bad. So what we decided to do is like, hey, we've got this server that's in a rack. Let's just do effectively a anycast loopback that we'll put on both spines and make that the next hop. Well, that's pretty good. That's cool. Hey, actually, that solves a whole lot of ECMP stuff too. So now actually we can actually get ECMP down to the rack. So it actually uses traffic goes down to both the top rack switch A and top rack switch B. And if there's a failure scenario, it just routes around it. And it uses the active link. So this was really cool. This actually works well. One of the other things we had, being a DNS company, we tend to do a little bit of anycast. And one of the other problems, again, it's the same thing because of iBGP and route reflectors. What's the best route when you have 4 or 6 or 10 anycast servers all announcing the same route? All of them. Well, no, only just one. Well, that's, again, not really what we call anycast. So we had to come up with something here, and we came up with different things. And the main thing we also want to do here is we didn't want a lot of network state. So we're not going to do something special for this. It can't be something that because of this server, we have to put something in. Because when the server moves or goes away or does something, you always forget about that state. So one of the things we did on this was kind of say, well, how many anycast routes will we have? And we figured it out, and we kind of went, maybe a couple of dozen at the most. That's kind of our maximum that we're seeing. Well, that's not really much, so screw it. We're just going to dump it into our IGP. Put them in OSPF. It's not a huge number. Hey, that gives us an ECMP. It just works. Cool. It just has to be good enough. So security. So our legacy data center does a standard security. We do ACLs, we have firewalls, and there's a problem. Things move, things change, and what happens, the network guys are always the last ones to know, it always gets blamed. Everybody always blames the firewall, everybody always blames the network guys. So, the answer was, just no more security in the network. So what we basically said is, okay, we're not going to do security in network. Well, we're not just going to do no security. No, we're going to actually push it all the way down to our instances, be those are the servers or the VMs. So what we basically told the squads is you guys are developing it, you guys own the service, you own the application, you also own the security for it. You guys have written it, you guys should know your own flows, so go and basically put that on there. Now the other cool thing was in the past, normally you put an ACL in front of a VLAN. Well, what happens if somebody gets in? Well, the blast radius is basically the VLAN. Here, the blast radius has been narrowed down to be a single instance. So, hey, this is cool, this is actually much better. Oh yeah, and it's less work for us, so it's less network state. So again, kind of making things easier, less stuff that breaks at 3 a.m. Now, of course, when we're doing this, we got to figure out a way to basically deploy the security in an easy way. So one of the things we do is we're using a lot of our continuous integration pipeline for this. So effectively what happens is when we first build a server or VM, we'll actually install base security right away. And that base security is effectively monitoring an SSH, so the guys can get into the box. That's it. Now the service owners themselves will have to go in, and because we use Chef, they'll go in and add to the cookbooks what they need opened up. And one of the things we're trying to do is to encourage them to be as restrictive as possible within reason. Because it's all automated, we can make things, it's a bit easier to deploy and so on. If we're deploying a Cassandra cluster where we've got 20 nodes that are all doing the same thing, one cookbook applied to all 20, thank you very much, have a nice day. One of the other things we're doing here is also automate audits and verification because we know people get lazy. So we kind of need to remind them that, please don't be stupid. So unfortunately, this wasn't the best because people really didn't like having to do more work. Before it was really easy. The network guys just took care of it, and we could blame somebody else, and we could, have it as being their work. So it actually took quite a long time to convince a lot of our service owners or developers that basically this is actually a good thing. And what's really surprising is one of our most vocal critics who had many loud discussions with me, at the end of it was completely on board. So this is actually possible. It just takes a little while for people to fully realize this. Now the final thing we had to think about was service mobility. So now we have a whole layer 3 network. We do different subnets for each rack. Well, what happens if something has to move? So I'm moving from one to another. I'm going to change IPs. Well, that kind of works, but doesn't really. Remember, we're doing IP tables, which are all IP address based. Yes, I know my examples are only v4. There wasn't enough room here to draw in a v6 address and still make it readable. It's like, well, what if we didn't have just the interface IP as what the service uses? What if we had this thing called, have a service address, an address for the service itself that isn't tied necessarily to an interface? So we did this thing of service IPs. Basically create a dummy zero interface on our Linux boxes, and we'll use exabgp, and the instance, again, this is being a chef cookbook that just gets deployed when everything gets built, and it's just going to announce the IP address or addresses that are bound to it, and there's your service. That seems like a really cool idea, and it really was, and for a bunch of stuff it worked really well. And then we deploy a Cassandra cluster that really does not want to bind outbound traffic to any particular interface, and it all fell apart. So this is one of these things that when it works really well. Unfortunately, it doesn't work for everything. We could have done fancy stuff to try and get everything to do this. Well, you do as much as you can. But overall, this actually worked. This worked pretty good, and for a lot of times, this is again one of those things where the developers up front really don't like this because it's more work for them up front. But when all of a sudden something goes down at 3 a.m. and we have to spin a VM or server up in another rack really fast, this will make life a lot easier because there's a whole lot less stuff to change. So one of the other things we did here when we were doing this is we wanted to basically also make sure that this stuff was easy to deploy, but more importantly, it's also easy to expand. Remember this whole, we're going from 20 to 200, we want to grow by an order of magnitude. So the whole idea is we're not going to go in and manually configure stuff. This really sucks. Really hate manual configuration almost as much as I hate layer 2. So one of the things we did is we automated all this. So hi Carlos. So we use Kipper, which Carlos talked about back in NANOG 63. Effectively, all of our top-of-rack switches are fully automated. If you go in and make a manual configuration, it'll be overwritten. So everything there is done. So if we want to add another 100 racks, not really a big deal configuration-wise. Rest of the network, it's getting there. It's sort of what we call kind of, partially manual, partially deployed. The idea is we want to move completely to 100% automated network deployment, basically just to make life easier for ourselves. And because so many things are so common, so this is really making life a lot easier, particularly when we have to do, we have to do this one little change across so many devices. Oh, well, that's no big deal. We should do a simple Kipper push, and there off it goes. So I want to talk a little bit about some of the things that we learned. I mean, this is like, pretty basic, but, design that's actually documented in advance, hey, there's a concept. One that actually can be implemented, that's even better. Trying to use M+ VPNs when you don't have 6VP support, bad thing. The other thing is that there's always a tendency to kind of, let's take the easy way out. Oh, we'll fix it later. You'll never fix it later. We never fix it later. The only time we fix it later is when we rip it out and replace it. So let's try and design it right. We try to validate as much as we can before we deploy. Never enough, but anyway. Integrating the legacy stuff was really hard. The legacy cruft that we had, that was really hard. And like everything, everything's, your mileage may vary. Some things on the network side, cheap layer 3 switches, we all love them. Unfortunately, they come with limitations, rib size, fib size, TCAM, features. It's the same OS, except for this box, which doesn't do all of those things. The multiple routing tables, yes, they are a pain, won't lie. I would still do it the same way over again. A few of them was okay. Automation, oh my God, that rocks. Seriously, if you guys don't do automation, do automation. BGP communities, that's just a no-brainer. That made life so easy. Tag the route at the beginning, whack down the community. We do not have a single ACL or prefix list or IP access list in our network. Don't need it. It's all just based on communities. The other thing we learned, there's no such thing as partially in production. As soon as you put that first service on, it's live. All of a sudden, now you have to do change windows. And staff experience levels, really kind of important there. We learned we can't deploy something that people can't support. Security, moving the security to the instances, that was really the right decision. That was probably the best thing that we did. Commercial solutions to do that, they just suck. Really, guys, get your stuff together. IPv6 support, hello. We rolled our own. Why? Because we had to. We actually wanted to buy somebody else's. Nobody can actually do what we needed. Their scary thing was a bunch of people who actually developed the code, they actually don't know their own flows because they've never had to think about it before. So it's a real education and learning experience. We basically held the hand of a lot of our squads to get them on board. Yes, you will have to spend time with it. It's just how it works. What we learned about our users, they don't like change. Our users being our developers, the people who run the applications on our network, they really hate change when they have to do more work. So that was a big selling thing there. The other thing was we really had to be involved with our development squads, effectively almost embedded with them. There were meetings at least weekly with them to basically get stuff there. We were writing IP tables, cookbooks for them, doing all sorts of stuff. And actually, it was probably more work than actually building the whole network, which is kind of doing all that stuff. So, just kind of summing things up, there's many different ways to build data centers. This is what we did. This works for us, might work for you. There's that, YMMV. The main thing here also for us is that we're not in the network biz. Our network here is just basically to connect servers that run the apps that provide the services that our customers buy. So in the end, the network for us wasn't really the biggest thing. The users, the business, and funny enough, all our legacy stuff actually trumps all that. Why all the legacy stuff? Because we have to incorporate it. And our users, because they're the ones actually using it, and they're providing the services that really is our business. Thank you.
Hi, Chris Woodfield with Twitter. You'd mentioned the fact that you were having issues because the route reflectors could only advertise one route down to the clients. Was there a reason that you couldn't implement the add path feature to send more than one route down?
Add path is only supported in 9.0. Does not support work in routing instances.
Okay, fair enough.
We did think of that.
Hey, Andrei Chemikov with Athena Health. So if you put security down to an instance, do you ever have to deal with audit? And if so, how do you audit that?
That's why we do have a auditing tool in place to do that. It's similar to auditing a ACL or firewall rules in a stateful firewall. So we're not finding any difference there. And our internal security team is fully on board with this.
So do you have to audit each individual box, or you just audit the templates and assume they're properly deployed?
No, we actually have to audit down to the server level. It depends a little bit on what we're doing, but we actually do audit all the way down to what is actually deployed, not just what we thought was deployed.
And now with the service owners and potentially developers managing their own security, do you generally trust them in that sense?
Yes, because we all work for the same company.
Interesting explanation. Thanks.
Mike Joseph, Google Access. Not to sort of championed one of our own solutions, but Google open sourced a system a while ago called Caprica that's fairly useful for managing ACLs, and I noticed you mentioned that you weren't happy with commercial solutions. So I don't know if you've looked into it, but it allows you to generate ACLs both at the network and the server and the system layer. That would allow you to sort of have a common ACL framework and still push ACLs where you want them. And if you want them at the network layer, you can apply them there too.
Okay, thank you. We'll look into that.
Sure.
Thank you.